All right, welcome to The Explainer. So, you've probably wondered, right? How does your computer's brain, the super fast CPU, manage to talk to something like a slow-moving printer without just grinding to a halt? Well, today we're going to pull back the curtain on the really clever system that solves this huge, fundamental problem in computing. Yeah, this is the core puzzle we're tackling. I mean, your CPU is an absolute speed demon. We're talking billions of operations a second. But then it has to work with these, slow, clunky mechanical things, like a printer or even your keyboard. The speed gap is it's astronomical. So how on earth do they work together without the CPU getting totally bogged down?
Okay, so to really get our heads around the solution, we've got to first appreciate just how big this problem is. It really is a tale of two completely different speeds. You've got the lightning-fast world of pure logic inside the chip, and then you've got the slow, mechanical reality of the outside world.
So on one hand, you've got the CPU. Think of it like a Formula One race car made of pure logic, just zipping through billions of calculations every single second. And on the other hand, you have all your input-output devices, and they're more like a horse and buggy. They're stuck dealing with actual physical stuff, motors, sensors, you name it. We're talking orders of magnitude slower. It's not even a fair race.
Yeah, early on, engineers figured out pretty quickly that having the CPU try to directly micromanage these devices was, well, it was a terrible idea. Just imagine your CPU having to personally oversee every tiny gear turn in your printer. It's like the CEO of a huge company stopping a board meeting to go down to the mailroom and stuff envelopes. The whole company grinds to a halt. It's a colossal waste of time that the CPU could be using to, actually run your software.
And here's a perfect example of what I'm talking about. With some of those really early computers, the CPU was basically a board security guard for the keyboard. Its job was to just constantly ask over and over, "Hey, you pressed a key yet? How about now? Anything? No?" It did this by scanning the keyboard's grid of wires thousands of times a second, forever. Talk about a massive waste of processing power.
So what was the big, brilliant solution to this mess? It was elegantly simple, really. Delegation. It's common sense, right? Why have the CEO down on the factory floor operating the machinery? No, it was time to give the CPU a promotion. Turn it from a worker into a manager and let it focus on the big picture.
And this is where the device controller comes in. This is basically a dedicated little brain, a tiny, specialized computer called a microcontroller that's attached to every single device. Let's go back to our CEO analogy. The CPU is the CEO. They don't go down and operate the machinery, right? They just tell the department manager, "Hey, I need this file," or "print this page." Well, the controller is that manager for your hard drive, for your keyboard, for your network card, for everything.
And this is the absolutely crucial point. This is the big idea. The CPU doesn't control devices anymore. It just communicates with them. It stopped being a micromanager and became a true delegator. And that one simple change freed it up to do what it's actually good at, running your programs at mind-bending speeds.
Okay, so the CPU delegates tasks, got it. But how does that communication actually happen? Like, what language do they speak? Well, engineers came up with a kind of communication toolkit, and it boils down to two key choices that pretty much define how every modern computer is built.
So choice number one is all about addressing. How does the CPU even find the device it wants to talk to? Think of it like this. With the first method, memory mapped I/O, it's like every device gets an address on the same street as all your main memory, your RAM. But with the second method, isolated or port mapped I/O, it's like the devices all live on a completely separate street with their own address system. Simpler chips like ARM tend to use the first way, while more complex ones like the x86 chips in your PC can actually do both.
All right, the second big choice is, how does the CPU know when a device is finished with its job? The first way is called polling, and it's kind of annoying. It's like the CPU is a little kid in the back of a car constantly asking, "Are we there yet? Are we there yet?" It just wastes a ton of time. The much smarter, much more efficient way is using interrupts. With an interrupt, the device just politely taps the CPU on the shoulder when it's done and says, "Excuse me, I'm ready now." Way better, right?
So, faced with these two choices, what do modern systems do? Well, pretty much all of them go for the best of both worlds. They combine memory-mapped I/O, that's the simple one where devices look like memory, with the super-efficient interrupted-driven approach. It really is the perfect combination of simplicity for the programmer and high performance for the system.
Okay, so that's the theory. Now let's get physical and look at how this all actually gets built onto the motherboard.
because the way these connections are laid out has changed a lot over the years, all in the name of making that conversation between the CPU and everything else faster and faster.
If you look back to, say, the mid-2000s, motherboards had this really important chip called the Northbridge. Its whole job was to be a traffic cop, directing data between the CPU, the RAM, and all the fast devices. But here's the problem. As CPUs got faster and faster, that Northbridge traffic cop just couldn't keep up. It became a massive bottleneck. So what was the solution? It was pretty radical, actually. They just fired the traffic cop and moved its entire job right inside the CPU itself. This gave the CPU a direct, super fast highway to memory and other high-speed components. So you might be thinking, wow, this is a lot of complexity. We've got controllers and buses and integrated logic. Why go to all this trouble? Well, the answer isn't just about speed. It's about solving a total nightmare from the early days of computing that almost stopped the PC revolution in its tracks.
Seriously, just try to imagine this for a second. Imagine buying a mouse that would only work if you had an Asus motherboard, or a graphics card that was totally incompatible with your particular brand of SSD. It sounds crazy, right? But back in the 1980s, that was just reality. Hardware was a bunch of walled gardens where nothing worked with anything else.
And this next part is just wild. It's the perfect example of the chaos. You had two of the biggest computers of the era, the Apple II and the Commodore PET. And here's the thing, they used the exact same CPU chip, the MOS 6502. You could literally pull the chip out of one and stick it in the other and it would fit. But programs written for the Apple would instantly crash on the Commodore, and vice versa. So why?
Well, the problem was that each company basically hardwired their devices into the computer in their own unique, secret way. They all had a different map of memory addresses, so a programmer might write code that tells the Apple II to put a green dot on the screen, but when you run that same code on the Commodore PET, that same address might be connected to, say, the cassette player. The computer would try to interpret draw a green dot as rewind the tape, and the whole thing would just crash and burn. It was total chaos.
So, the solution that we have today is this really beautiful layered system. At the very top, you have the software. To the OS, it still just looks like it's reading and writing from memory addresses. Nice and simple. But underneath that, in the next layer, the CPU and the motherboard's chipset act as universal translators. They take those simple memory requests and convert them into a standard language. And then, at the bottom hardware layer, that standardized data travels over a standardized physical connection that everybody agrees on, like USB or PCI Express. And the final magical piece of this whole puzzle is the device driver. You've heard of them, you've installed them. That little piece of software is the ultimate translator. It's like a universal phrasebook that tells your operating system exactly how to speak the unique language of that specific graphics card or that weird mouse you just bought. This whole layered system, with drivers as the final link, is what killed that compatibility nightmare for good. It's why we can plug pretty much anything into our computers today, and it just works.
So there you have it. We've peeled back the layers on this hidden world of delegation, translation, and standardization. It's this incredible system designed to hide immense, mind-boggling complexity and just make things feel simple. So the next time you just casually plug in a USB drive, take a second to remember the decades of incredible problem-solving that went into making that simple little action possible. And it really makes you wonder, doesn't it? What other invisible, amazing translations are happening inside our technology every single second just to make it all work?